1, 2, there we go. So today is dark matter, but we have a few slides from last time. Since it's dark matter today, I have to wear my dark matter t-shirt to keep you focused. Okay, but there were a few slides from last time that I want to go over just on some basics of the cosmology, and that will be useful for the next couple of lectures. So the universe is isotropic and homogeneous. The expansion is just a rescaling, and so we have this thing called the scale factor, and so you can summarize the expansion of the universe just like that. It's just a conformal rescaling. And this is the scale factor, and in principle there are three kinds of evolutions. So there's an evolution where the expansion slows down and the universe falls back on itself. That's the high-density universe. Then there's the expansion that eventually stops slowing down, and the slope of this is constant. And then there's the Goldilocks universe that keeps slowing and slowing and slowing. And they vary with their density. We'll come back to this next time when we talk about dark energy. The story is a little bit more complicated. But what is absolutely true is that the high-density universe curves back on itself. So the curvature of space-time is related to the density. The low-density universe curves away from itself like a saddle. And there is a case that's in between the universe that's uncurved. As I said last time, that's our universe, and that's a universe that has a particular density called the critical density, and all densities are scaled relative to that. So the expansion is a scaling up. I call the scale factor R. Not everybody calls it R. Some people call it A, so don't be confused. And let's see, I think we talked about most of these parameters. The expansion rate today, which is about 70 kilometers per second per megaparsec in these funny units. The expansion rate, 1 over it is a time, and that's basically the time back to the Big Bang, so that's about 14 gigayears. It's also a distance, and that's sort of the size of the visible universe, so that's about 10 to the 28 centimeters. The total density over the critical density is called omega naught, and it's the sum of various little pieces. And here's the formula for the curvature radius of the universe. It's related to the density through this formula, so that if the density is the critical density, the curvature radius is infinite. It's uncurved. And this critical density is about 10 to the minus 29 grams per cubic centimeter, or in particle units, it's about 500 eV per cubic centimeter, or if you want to put it all in particle units, it's this number here. And the density, you're supposed to sum over everything, and we talked a little bit about that last time, the temperature of the universe, and you're summing over everything here, but the omega in photons is very small, about 10 to the minus 4, but we'll come back to that. Oh, and here's the famous second number, Q naught is, so H naught I should have put is R dot over R evaluated today. Q naught is the so-called deceleration parameter, the second derivative of R. To make it dimensionless, you divide it by the Hubble constant squared, and to make it have the sign that you think that it should have, not Hubble, but Sandage put in this minus sign. And it's related to omega divided by 2 times 1 plus 3 times the equation of state of stuff in the universe. And equation of state is just P over rho, and we'll come back to that. So if it's just matter in the universe, then W is 0, and Q naught is just omega over 2. And so that's what Sandage was imagining, that these two things were equivalent, and he liked Q better than a Greek letter. But if you have funny things in the universe, like for photons, W is a third, so then Q naught would be omega, and we'll also be looking at W equals minus 1. Okay, This is a fun slide. So this expansion of the universe, everything gets scaled up. Distances between galaxies, wavelength of a freely propagating photon. And so the redshift of a galaxy is 1 plus the redshift is the wavelength that's detected divided by the wavelength that's emitted, and that's directly related to the size of the universe today over the size of the universe at the time when it was emitted. So when we find a galaxy with a very big redshift, what the redshift measures is not the age of the universe. That depends upon the expansion history of the universe, but it actually measures the size of the universe back then. And I'll show you a couple of spectra here that are really fun. The momentum of particles also redshifts. So the momentum of any particle, be it a photon or be it a slowly moving hadron, goes like 1 over r. And so that means that as the universe expands, photons get longer in wavelength, get redshifted, go to lower energy. Distance between galaxies. The only thing that doesn't scale with this are gravitationally bound systems or electrically bound systems. So galaxies don't scale up in size, nor do clusters, nor do atoms. So this is fun. These are some of the most distant objects that we see and can easily take spectra of are quasars. And so now I can teach you everything I know about a quasar spectrum. And then you'll be able, if somebody shows you a quasar spectrum, you'll be able to take a redshift in nanoseconds. So quasar spectrum looks qualitatively like any one of these. There's a big whopping feature, and that's Lyman alpha emission at 1216 angstroms. And then there's a plateau up here and various important atomic lines, oxygen, magnesium, etc. And then blueward, or to short wavelengths of the Lyman alpha, the spectrum drops dramatically, particularly for distant quasars, because of all of the absorption of all the material intervening. And so this is, these are 3 quasars at redshift 5.8, 6.0, and 6.2. And to get the redshift of a quasar, all you need to do is look at where that big whopping Lyman alpha feature is, and take that number, divide it by 1216, and that's 1 plus z. And so it's very easy to get the redshifts. This object, this z equals 6.2, is not the most distant quasar. This one is. It was found by a theorist in the Sloan Digital Sky Survey. I was asked, I was shown some data, and I said, why is there an arrow pointing to that object? And they said, well, that's a good question. And they went and took the spectrum, and it was a 6.4 quasar. So apparently high redshift quasars have objects near them that have the shape of arrows. And
objects in the line of sight.
Sorry?
Objects in the line of sight.
Yes. Yeah, that's amazing. Do you think that somebody actually puts those arrows in, that they aren't there on the sky? Anyway, what's stunning about this is this radiation was in the UV and invisible to the human eye when it left that object. It has now been redshifted all the way out to roughly 10,000 angstroms. It's now in the infrared and invisible. And so, for example, this quasar here, the light was emitted when the universe was 7.4 times smaller. So this is absolutely stunning. This is in astrophysics, we, just like in race cars where there's a land speed record, the fastest. So we have the highest redshift object, and to get the highest redshift object, you don't have to go to Bonneville and race 1 mile and turn around and race another mile. You just have to have a sort of a spectrum, and this is the highest redshift object. It was a spectrum taken of the afterglow of a gamma ray burst that occurred in April of, roughly 1 year ago, April of 2009, a redshift of 8.2. And here's the spectrum. So there's some light at Lyman alpha and then very little light intervening because it's been absorbed by the intervening universe, and the estimated redshift is 8.2. So this is the highest redshift object where there's a reliable spectrum. Let's see, I already talked about this, the three different kinds of universes, and we know this one is ours, so we don't have to worry about non-Euclidean geometry. Here are the equations from general relativity for this very simple solution that's isotropic and homogeneous and is just a rescaling. The equations are very simple. So there are two equations. They're called the Friedmann equations. And in the language of John Wheeler, matter tells space how to bend. In this case, it can only bend one way. It just gets bigger. And so the expansion rate is equal to 8 pi g rho over 3, where rho is the total density. And let's see, I've taken out, I've written this for a flat universe. In a non-flat universe, there would be a term involving the curvature radius here. And then there's a second equation that is mathematically equivalent to the first equation that looks a little friendlier. It looks like F equals ma, so the second derivative, or the acceleration of the expansion, is driven by minus 4 pi g times rho. If that were the only term there, that would look like the Newtonian, Newtonian gravity. You could derive this from Newtonian gravity. But in general relativity, there's a separate piece here, the gravitational attraction, or the gravitational force of a spherically symmetric system, if you set it up and try to describe it that way, depends not only upon the mass and energy, and according to Newton, it's only the mass that determines the gravitational field. It also depends upon the composition through the pressure. And so rho plus 3p is what sources gravity. And we'll come back to this next time. If you had some weird substance like vacuum energy that had negative pressure, then rho plus 3p is negative, and the gravity is repulsive, and you can get an accelerating universe. Okay, so the second part of this story is space tells the matter how to evolve, and so here are those equations. So, I see, we're missing an equation here. This is covering. Let's see. I'm sorry. Maybe if I press the button, the equation will come. Okay, the equation came. I'm slightly confused here. So space tells matter how to move. And so in this very, very simple model of the universe, conservation of stress energy is expressed by the divergence of the stress energy tensor. And because there's so much symmetry, it just reduces to this, that d, the change in rho r cubed, so that's the energy in a co-moving volume. So if you watch a volume that gets bigger with time, that's the energy within that volume, is equal to minus pdv. So it just looks like the first law of thermodynamics. And if you assume that the pressure is equal to W times rho, so W is this equation of state parameter, then you can just pull out of this that rho evolves as R to the minus 3 times 1 plus W. And so if W is 0, just for matter that has very little pressure, rho goes like R to the minus 3, and that's incredibly simple and intuitive. The density of matter just dilutes as the universe expands. On the other hand, and I'm sorry, and then if we go back to this equation here, and plug in that solution for rho, the scale factor grows like t to the 2/3. For the case of radiation, where the pressure is 1/3 the energy density, then rho goes like R to the minus 4. Now, you could have anticipated that, because if you have a box full of photons, their number gets diluted as the universe expands, and their energy gets redshifted. And if you plug that in to the first Friedmann equation and ask how does the scale factor evolve, it grows like t to the 1/2. So it evolves at a different rate. And if you take the case of p equals minus rho, or vacuum energy, first of all, if you look up here, you find that rho is constant, And then if you ask, how does the universe evolve, the scale factor grows exponentially. Okay, so let's come to the universe that we've been given. And this is either log of scale factor or log of redshift. They're just the inverses of one another. This is log of energy density. Let's start out with vacuum energy. It's really easy. It doesn't evolve with time. Then there's matter that evolves like r to the minus 3 or 1 plus redshift cubed. And then there's radiation that evolves like r to the minus 4 or 1 plus z to the 4th. Okay, and here we are today where the amount of vacuum energy is about twice the amount of matter, and the amount of radiation, notice this is a log scale over here, is 4 orders of magnitude down. This mix changes with time because the different components evolve differently. And so you can see that from now on, assuming that the dark energy really is vacuum energy, we will be vacuum dominated. But in the recent past, redshift 1 and higher, we were matter dominated. And then eventually, and this is roughly equal to redshift of a few thousand, about 5,000, the radiation wins out and we're radiation dominated. So there's 3 epochs. There's an early radiation dominated epoch when the scale factor is less than about 10 to the minus 4 and the age of the universe is less than about 10,000 years. Then there's this matter dominated epoch, and then there's the present accelerated epoch. Now, of course, in the last lecture we'll talk about inflation. So maybe there's evidence that there was an earlier accelerated epoch. And so 3 epochs. This matter-dominated epoch, I'm not going to have very much time to tell this story, but during this phase where matter is dominating, this is where a lumpy universe grows structure, where the lumps in the universe are pulled together by their excess gravity, and they make all the structure in the universe. And if once we get into this phase, when the universe is expanding exponentially, the clumping of matter can't keep up with the expansion rate, and so whatever structure is there, and no new structures are built. During this radiation-dominated phase, likewise, structure can't form. So there's this short period of time, roughly 10 billion years, or a little more than a factor of 1,000 in the growth of the scale factor, when structure can grow. And I think I mentioned this last time. One of the stunning consistency tests of this standard cosmology is that the gravitational amplification of small inhomogeneities during this matter-dominated phase is just enough, is just right to take these initial density perturbations and see them and grow them into the structure that we see today. And I'm going to come back to that in a minute. This early radiation-dominated phase, so we certainly have photons, and this setting h bar and c and k Boltzmann equal to 1 is the energy density in photons, just goes like t to the 4th. Here's the number density of photons. But as the temperature rises, we can also pair produce other massive particles. And so as we go to higher and higher temperatures, there are more and more particle species participating, so that the total energy density goes like a quantity called G star, which just counts the number of degrees of freedom, times pi squared t to the 4th over 30. And so we can now ask what was in that quark soup. And here is a plot of G star going back to higher and higher temperatures. And so it gets bigger and bigger. And we can put in, here we are today with neutrinos and photons. When the universe had a temperature of about 1 MeV at 1 second, then we have the E plus E minus pairs. The quark-hadron transition at a temperature of a few hundred MeV dramatically increases the number of degrees of freedom. And then if you go all the way up to 1 TeV and count all of the degrees of freedom of the standard model, I think you get a number like 106.25. And of course, as you go to higher and higher temperatures, there may have been more and more degrees of freedom. Right. And so for this radiation-dominated universe, the scale factor grows like t to the 1/2. This is the formula for the expansion rate. And, you know, I don't know if banks in Switzerland have this, but in America, banks always have a time-temperature sign. And the time-temperature sign for the universe is the temperature in GeV is the time in microseconds to the -1/2 power. Okay, so now we're going to move to the dark side. And just to remind you of some numbers, light, luminous matter in the universe, stars, is only about 0.5%. And then in round numbers, the dark matter is about 1/3 and the dark energy is 2/3. And so we'll talk about the dark matter now. And so I'm going to walk you through the evidence for dark matter that starts with astronomers. And basically, its gravity is needed to hold structures in the universe together. Zwicky looked at clusters, Vera Rubin and others. So Zwicky did that a long time ago, 1935, and Vera Rubin and others since the 1970s looked at galaxies. So let me just quickly take you through that evidence. Zwicky looked at the Coma cluster. I showed you this beautiful picture of Coma the other day, several thousand galaxies. But let me just show you how these clusters are found on the sky. So this is an image of the sky. It's not an image of the sky. It's a representation of galaxies on the sky. And this is 10 degrees, and I guess 10 degrees, 12 degrees in this direction. So this is a big hunk of the sky. The dots are galaxies from a certain catalog of galaxies that doesn't go very deep. And so you see in many places you just see a uniform density of galaxies. And then in some places you just see an overabundance of galaxies. And George A. Bell, right here, Zwicky and then after him A. Bell, looked at these photographic plates and pulled out clusters of galaxies. And here's the Virgo. That's one that's very close, so it looks very big on the sky. We have applied for membership in the Virgo cluster, and it looks like the committee has approved us, so we're falling into Virgo. We're not quite a member of it yet. This is the Coma cluster. It looks very small because it's actually bigger than the Virgo cluster, but it's much farther away. And let's see if there's any other. There's another cluster, Abell 1367. But let's go back to the Coma cluster. And so you know the story probably that Zwicky measured the random motions of galaxies within the Coma cluster, and the velocities are quite big. Thousands of kilometers per second. And remember, when I was going through the history, until the early part of the last century, the velocities that astronomers measured were of order tens of kilometers per second. And so this is a very, very big number. And so what keeps this cluster together? Well, in principle, the gravity of all the stars of all the galaxies. And so Zwicky did that calculation. And that misses by almost a factor of 100. And the formula for figuring out the mass that you need looks very Newtonian. You use the virial theorem to get this, but the mass you infer is basically the size times the velocity dispersion divided by Newton's constant. And he found that there was a factor of 60 off. And he said, okay, there must be more to clusters than meets the eye. And this problem didn't catch on in the 1930s. Partly it was because cosmology was new and the sky was wide open and there was lots of stuff to worry about. And maybe clusters weren't even bound objects. Maybe they were accidental superpositions on the sky. Partly it was his personality. Very, very smart guy, very, very cantankerous. Here he is giving a visual description of spherical bastard. Maybe some of you know what a spherical bastard is. It's a person, no matter what direction you approach them, they're a bastard. And So the problem didn't really catch on until 1970, and Vera Rubin brought the problem closer home and was measuring rotation curves in galaxies. And this is the Andromeda Galaxy. And so, roughly speaking, in a galaxy, the stars move around the center of the galaxy. When you get out here, there are a handful of stars and gas clouds that you can trace. And so you can make what's called a rotation curve, which is just the circular velocity versus distance from the center of the galaxy. And what was stunning, and what is still stunning today, is that these rotation curves are flat. And if all the mass were associated with the stars at the center, eventually you would see what's called the Keplerian fall-off of V going like 1 over the square root of R. And such a rotation curve like this means that the mass continues to rise. And, you know, I made up this slide a very long time ago when there were 967 flat rotation curves and still counting. So no rotation curve has been seen that turns over. This is kind of one of our poster childs. Let's see, this is NGC 3198. Here's this beautiful rotation curve. Here is the rotation curve you would expect if you only put in the bright material in the disk. And so you can see that it would be falling off like 1 over the square root of R. If you add in a dark halo, you can reproduce the rotation curve. And here is the part of the rotation curve produced by the dark halo. And so you need the dark matter to keep the rotation curves flat. I'm going to come back to this and mention this a little bit later on. These are a bunch of rotation curves, and this red line is where the visible light has gotten negligible, where it's 1% of the light at the center. And you can see that galaxies come in different sizes. And the need for dark matter in different galaxies, in different sized galaxies, occurs at a different radius. And so if you were thinking about a solution of gravity getting stronger at a certain distance, that simple-minded model simply would not work, because different galaxies need dark matter at different distances. This is just the rotation curve for the solar system, perfect 1 over the square root of R. These are rotation curves for matter around black holes, where you have a central black hole and then you measure the velocity of stars nearby. Falls off like 1 over R. 1 over the square root of R. Here's the rotation curve for our own Milky Way. It's hard to measure your own rotation curve. The data are not particularly good, but even here you can see a flat or slightly rising rotation curve for our galaxy. And so the long and the short of this is that you can only explain the motions within galaxies if you have this dark halo whose density goes roughly like 1 over R squared. And I apologize for this image. This is not a real image of a dark... Well, actually, it's a pretty good image of a dark halo. And so the idea is that the visible part of the galaxy is immersed in this dark halo. Sort of the most problematic thing about this slide, other than that it's overexposed, is that our dark halo is more than 10 times larger than the visible part. The dark halos are enormous. In fact, our dark halo basically extends to our nearest neighbor. And we can even determine for our galaxy the local density of halo material. And it's about 10 to the minus 24 grams per cubic centimeter. And this will come back with dark energy. So the local density of disk material is about 10 times greater than that. And so the halo wins because it just goes on forever. So it's the tortoise, not the hare. So the halo is very, very big. And so while where we live in the galaxy, the halo density is about 1/10 that of the material in the disk, since it keeps going on forever, or not forever, but since it keeps going on, the mass keeps piling up. If you look at a density that goes like 1 over r squared, the mass is growing like r, and that's just what you need to produce the flat rotation curve. You can map the dark matter using gravitational lensing. This is a technique that Tony Tyson pioneered. This is a Hubble image of a cluster whose phone number is here, 0024 plus 1654. And the cluster galaxies are orange. And well beyond this cluster of galaxies, there are fainter galaxies, named by Tony Tyson faint blue galaxies because they're faint and blue. And if you look at these faint blue galaxies that are well beyond the cluster, they look funny. So here you have ring-like galaxies, a whole bunch of them. If you look at the, let's see, where do we want to go? Look at this faint blue galaxy. It's highly sheared. And what's happened is that the light has been distorted because it's passed through the gravitational field of this cluster and been bent, and the cluster acts like a lens. And if you want to make the kind of lens that a cluster is like, you want to go down to the cafeteria, get a wine glass, break off the top of the glass, and the bottom of the glass has the right curvature so it acts like a gravitational lens, and then, put it on top of a picture of galaxies, and you'll see these same kinds of distortions. And from this, you can map out the distribution of matter and find the mass of a cluster. And this is, again, work of Tony Tyson. So what you actually map out is the mass per area. And so this two-dimensional image on the sky here is the two-dimensional mass distribution. The technique is so good that you can actually pull out the individual galaxies, and they look quite spectacular, but most of the mass is in this smoother distribution, and so that's the dark matter. So you can map out the dark matter in clusters of galaxies. Okay, let me just summarize, put all in one place what we've learned, or the evidence for dark matter. So it's the flat rotation curves. So galaxies have big dark halos that hold them together. Clusters are held together by dark matter. In some ways, the evidence here is even more impressive because we have 3 ways to estimate the mass. I mentioned the galaxy motions and using the virial theorem. I mentioned lensing maps. The technique that I didn't mention, I'll show you an image in a second, is that galaxies are filled with hot X-ray emitting gas. And so you can apply the virial theorem to that hot X-ray emitting gas, and its velocity dispersion is just measured by the temperature. And so these 3 different masses agree and are much smaller than the amount of mass in the stars or even the amount of mass in the X-ray gas, which I'll come back to. Let's see, I've got a slide on the CMB, Big Bang nucleosynthesis, census of stuff in the universe. And I'll show that next. Without the gravity of dark matter, we cannot explain the structure in the universe. That's a pretty big piece of, without the gravity of particle dark matter, we cannot explain the observed structure. So let me hit these 2 points in more detail. So to remind you, the CMB and Big Bang nucleosynthesis determine this combination of parameters, omega bh squared, to be 0.021 plus or minus 001. The CMB and maps of large-scale structure like the Sloan determine omega matter, where matter includes anything that gravitates, to be omega matter h squared to be 0.13 plus or minus 0.005. And the difference between, let's see, first of all, these 2 numbers are not equal, right? And the difference between them is 20 sigma discrepancy. So when we do the accounting of baryons and when we do the total accounting of matter, they differ enormously. So I would say that this is airtight evidence that there's something out there beyond baryons, or we have a very serious problem with gravity. Let me come back to structure formation. It's the matching of the density and homogeneities that are amplified by gravity. So this is an example of a numerical simulation that give the observed structure today. In the case where we have particle dark matter, the density perturbations can start growing as soon as the universe becomes matter-dominated, because the particle dark matter doesn't couple in with the photons, and so you can get the right amount of growth to turn this into that. With baryons only, the baryons are trapped by the photons. They're interacting with the photons, and the photons won't let them collapse until the the epoch of decoupling, redshift of about 1,000. And so you get a growth of only about 1,000, and you can't make this. You can't grow the structure we see in the universe from these perturbations with that amount of growth. So again, I guess one way to put it, these two slides, one way to put it would be, if we don't have particle dark matter, the entire framework is messed up. Okay, the numbers. So just to remind you of the numbers, there's actually several dark matter problems. So first of all, stars weigh in at about 0.5% of the critical density. Atoms, as we talked about, are about 4.5%. So most of the atoms are actually dark to the visible, to the human eye, or don't give off light in the visible. So we've got a bunch of dark atoms, about 4% of the total, so that's just the difference of this number and that number. And we believe that's in hot gas. I'll come back to that in 1 second. Then we have, if you look at the total amount of matter, which is about 27%, we have 23% of it that's non-baryonic, particle dark matter, exotic dark matter. And then we'll come back to this in a second. We already know that some of the dark matter is neutrinos. We have a lower bound based upon our knowledge of neutrino masses, and also an upper bound based upon our knowledge of neutrino masses. Neutrinos are in the same ballpark as stars are, but they don't explain the bulk of the dark matter. And I would say that what's interesting about the neutrinos is, and I don't know if you know this saying, in the United States we used to have these salesmen that would come to your door, the Fuller Brush man, and he wants to get his foot inside the door, because once his foot is inside the door, then he can get in your house and then he can sell you something. And I would say the fact that we have good evidence that the neutrinos are at least part of the dark matter is the foot in the door, that this idea that there's something out there other than atoms is not completely crazy. Okay, clusters. Let's see, let me go forward here. So this is an image that maybe some of you have seen. This is the collision of two clusters. It's called the bullet cluster. It was once called the best evidence for particle dark matter. I don't really think that's true, but I think it's nice to illustrate the fact that clusters give us a fair sample of the universe, and then we can look and see if the numbers we get for the cluster agree with the numbers we get for the microwave background. So here is a cluster. Well, this is a collision of two clusters. So you can see the hot gas, so that's in red, and by measuring the total X-ray emission, you can estimate the total amount of gas. Then by using gravitational lensing, you can infer the total amount of dark matter. And here it's shown as blue, and it's these two clumps because the clusters have collided and gone through one another. And then, of course, the images, the pretty images, are galaxies. And let me go back here. So we can do this for a variety of clusters. And here are the percentages that we get. That stars are about 2% the cluster's mass. The hot gas is about 14%. The dark matter, I hope these numbers add up, is about 84%. I think they do indeed add up. And this is consistent with the universal mass ratios that I just talked about, that omega stars is 1/2, that omega hot gas is 4%, and that the exotic dark matter is 23%. So in a cluster, we see the universal mix. We would expect this because clusters are big. We have a saying in the United States, bigger than a kitchen sink. So everything would have fallen in. And so they give us a fair sample of the universe. And if we didn't see a ratio that was consistent with what we got from the microwave background, we would be a little bit worried. Now, the one caveat here, a big interesting problem in astrophysics is where the missing baryons are. In a cluster, we found them. They're in a hot gas. But I mentioned earlier that only about 5% of galaxies find themselves in a cluster. So one of the hot problems is to find the non-stellar, the non-luminous baryons associated with a galaxy like ours. And we think that they're in hot gas, but because our galaxy has a shallower potential field, the gas is not as hot and it's hard to see. It doesn't glow in X-ray. Okay, let's see. What did astrophysics tell us about the dark matter? This was the point I made earlier. The need for dark matter comes at different length scales. And I don't want to dwell on this, but it first of all tells you that if you had a simple theory that there's no dark matter, it's just gravity getting stronger at longer distances, that theory just doesn't work. And it doesn't work because small galaxies need their dark matter at a short distance, big galaxies need it at a larger distance. Morty Milgram in 1983 pointed something out that he continues to remind us until this day. Whether or not it's just a coincidence or an important fact, I don't know. I actually think it's just a coincidence. That the dark matter kicks in at a certain characteristic acceleration, at a value of v squared over r equal to 10 to the minus 8 centimeters per second squared. And remarkably, that's also equal to the Hubble constant. And so he had a whole, I don't even want to call it a theory, but he had this thing called MOND, Modified Newtonian Dynamics, where his idea was that at low accelerations, F is not equal to ma, F is equal to ma squared. And if you just work the numbers, if you assume that F is equal to ma squared, you can get flat rotation curves even though there isn't any more matter. Unfortunately, this theory does a fantastic job of accounting for rotation curves, but we know more about the universe than rotation curves. And so I think I've spent too much time talking about this, but this is a very interesting fact. And this cold dark matter theory of structure formation, which I told you about, better be able to account for this. I once wrote a paper on that, and I hope that it would be, would drop out, not miraculously, not a coincidence, that it would just jump right out, and it didn't, but it did come out. But this is an interesting fact. The dark matter is less concentrated, and what that simply means is that it's very weakly interacting. The ordinary matter is concentrated because if you look at our galaxy, in the halo, the ordinary matter was once as diffuse, but the ordinary matter has atomic interactions, and through collisions it loses energy, doesn't lose angular momentum, and it goes down to the spiral structure that you see. And so, roughly speaking, we know that the dark matter must be weakly interacting, not meaning the weak scale necessarily, but certainly meaning that it's uncharged. If it were charged, even if it were in sort of atomic form, it would have cross-sections big enough that it would condense. We know from structure formation, this cold dark matter theory of structure formation, that the dark matter particles must be cold, and what that means is have small velocities. If they had big velocities, then they would run out of the density perturbations in small structures, and only big structures would have formed initially, like clusters. And that's what happens if the dark matter were neutrinos. And so that's another fact we take away. And then this last fact that I keep coming to is this accounting problem that it must be non-baryonic. And it's even more than the accounting problem. If it's baryons, where are they? And we could go through a list of, it can't be faint stars because we've now used the Hubble Space Telescope to look for faint stars in our halo. It can't be dust. if there were enough dust to explain the rotation curves of our galaxies, we wouldn't be able to see out of the galaxy, and so on and so forth. So it's really two separate arguments. Okay, so over the years we've had we've gone to focus groups and asked what could the dark matter be. I didn't include Zwicky's list. Zwicky had an interesting list, but when I want to, at one point, this was interesting. Astronomers were upset that there were way too many cosmologists, and so they suggested that maybe the dark matter is relic cosmologists. But the infrared background from relic cosmologists would produce too much light. So I think you probably all know this one, that this is a diagram I drew in 1990. I think it's on the back of this T-shirt, but it's impolite to face my back to you too often. We're focusing on an axion. I'll talk a little bit about that, neutrinos, and certainly the neutralino, but more generally something called a WIMP, a weakly interacting particle, a particle whose interactions are weakly interacting. The neutralino would be the best defined of these. And the neutrino story is pretty much completed. We know that the neutrinos are a cosmic spice, but not most of the dark matter. And so let me just remind you how we got these relics. So at the beginning of today's lecture, I talked about that hot phase early on where we'd have thermal democracy. Any particle species whose mass is less than kT would be present in big abundance. And so if you look at the ratio of a particle species relative to photons, and this is a temperature scale that goes high, this is 1 over temperature. So it starts out at high and goes to low. So at high temperatures, this thermal democracy, at low temperatures, if equilibrium were maintained, the particle species would annihilate away. Pair production wouldn't work anymore because the average energy of particles in the universe is not enough to pair produce them. And so, in principle, we should have nothing left over from this early epoch of thermal democracy. In practice, we know that if you have a particle species that weakly interacts, it doesn't follow this green curve. And in fact, it doesn't get the message that it's supposed to annihilate. Its annihilation cross-section is too small and just doesn't disappear. And neutrinos are an example of a particle that decoupled from the thermal bath while they were still relativistic, so their abundance today should be roughly that of photons. And then we'll focus on the WIMP. The WIMP is a particle that goes down this curve and eventually stops annihilating. And so the neutrinos are a very simple story. We can calculate their relic abundance to 3 significant figures. Here's the formula for omega. It's the sum of the masses divided by 91h squared, and I told you h squared is about a half. So this is sum of the masses over 45. And then just reminding you what we know about neutrinos. We know they do have mass because they oscillate. So we can place a lower limit on omega of about 0.1%. We have direct measurements. The Mainz measurement of the electron neutrino mass, if you multiply that by 3, you get an upper limit of about 13%. I mentioned that neutrinos are not good for the structure of the universe because they wash out structure on small scales. And so based upon the structure in the universe, we probably have a robust upper limit of about 2%. So the neutrino story is just about done, somewhere between 0.1% and 2%. And I'll just skip over that slide. This just summarizes that the data that have been used to... I forgot to put that in. Let me go to this slide. So it's studying structure in the universe that has put better limits on neutrino mass for the sum of neutrino masses than the direct measurements. And I arbitrarily put this number at about 1 eV today. What's interesting is that these methods up here, use, and we'll talk about this next time, the baryon acoustic oscillations, or the imprints of those acoustic oscillations on the matter-power spectrum. And that technique if fully exploited, might get down to neutrino masses of a few hundredths, might get down to where we really think the neutrino masses are. And I'll mention that next time. Okay, so let's come to the WIMP. And please remember that the WIMP is trademarked, and there is money that needs to be paid to me every time you use it. And so here is the story. It's incomplete annihilation. And the story is a very simple one. As a particle species tries to follow this equilibrium abundance curve, they're getting rarer and rarer. And eventually they reach the point that given their annihilation cross-section, they don't find each other to annihilate, and their abundance, the term we use, freezes out. And their abundance relative to photons from that point forward just is constant. And if you think about it, this is survival of the weakest. So if you have a big annihilation cross-section, you stay in equilibrium longer and you have a lower abundance. If you have a smaller annihilation cross-section, then you freeze out earlier and have a bigger abundance. And the formula is very, very simple. The surviving number of particles is inversely proportional to the annihilation cross-section. And then there's the mass of the particle and the Planck mass. And then if you ask, how do I get omega equals 1? It's an annihilation cross-section of order 10 to the minus 36 square centimeters, or of order the real weak interactions. And this is sometimes called the so-called WIMP miracle. And this is what sort of implicates and makes this new machine that was built here. Isn't it called the dark matter factory? Because isn't the French, I mean, you have to translate LHC into English, and LHC is the French for dark matter factory, isn't that? Okay, I didn't take French in school, but... Okay, then there's the axion, and I don't have time to talk about it, but I want to mention the axion because it's not a thermal relic. It's produced in an entirely different manner. It's produced coherently. It's produced in a Bose condensate. So even though it's very, very light, it's very, very cold. And it's the particle that sometimes gets forgotten. It's a fun particle because there's all kinds of neat astrophysics that you can do to it. There's analogies between axions and rock stars. Axions help stars lose their free energy. Well, anyway, that's a story I could tell at lunch. And if you look at what the universe has taught us about axions, it's taught us that there's a tiny little window here around 10 to the minus 5 eV where they could be the dark matter. And, okay, let me just finish up today with the front side of my T-shirt, desperately seeking dark matter. And I think my summary slide, which I'll get to in 4 or 5 slides, is that this is the decade of WIMP dark matter. May even be the decade of dark matter. Is that this is March Madness in the United States, the college basketball. And so do you all know about a full court press? You know, the really good teams, when they're playing defense, they play defense the entire full court. So that means... And so the full court press that we have on dark matter is, first of all, producing them at an accelerator, and that would be the WIMP. Because that cross-section, for the neutralino, we can actually calculate it, assuming you know the parameters of supersymmetry. But more generically, the cross-section to annihilate into ordinary particles is of the order of 10 to the minus 36. And the mass is of the order of a TeV. And so that should be a particle that, even if it's not a neutralino, if it's something more exotic, should be producible at the LHC. Then there is direct detection. So our halo is filled with neutralinos. Roughly speaking, if neutralinos are the dark matter, in every coffee cup, there's about 1 neutralino. Then there is the fact that the neutralinos, or the WIMPs more generically, can bump into one another with this 10 to the minus 36 square centimeter cross-section and produce interesting particles that are easier to detect: photons, electrons, positrons. And so we have instruments that are looking for them: the Fermi Gamma Ray Space Telescope, looking for high-energy gamma rays; Pamela, and soon to be the AMS experiment, looking for the positrons. And if they annihilate in the sun, if they accumulate in the sun and annihilate, the high-energy neutrinos could be detected by ice cube or a big kilometer-cubed neutrino detector. So right now, this is the dark matter factory, and it's probably not going to detect dark matter. It's probably explored all of the space that it has. This is, I wish I could remember how the LHC, so how those letters, well, anyway, somebody at lunch will tell me about how the French words that LHC actually means dark matter factory. And I'm realizing that I'm getting in a lot of trouble here because my host, of course, is, well, here's the beautiful Atlas detector. Oh, I guess it's CMS. But their picture is prettier. Okay, and the axions, just to finish up here, the axions involve this conversion of an axion in the presence of a strong magnetic field to a microwave photon, an idea of Pierre Sakivi's. This pioneering experiment is at Livermore National Lab, but I think there's a truck at Livermore that wants to move it to the University of Washington. I apologize for not... Sorry? And this experiment is a marvelous experiment. So far, they have succeeded in building the most sensitive microwave radio receiver ever built. And what's stunning about this experiment, so the power level that they're sensitive to is 10 to the minus 23 watts. What's stunning about this experiment is that if those pesky little theorists could tell you where the axion mass was, they could have already detected it, because once you have a resonant cavity and you just need to tune to the frequency, and if you knew the mass determines the frequency, within a few hours you could detect the particle. But if you don't know, if you're searching blind, then the fundamental parameter, quality parameter for an experiment is your scan rate, how fast you can scan. And, of course, you have to scan to the right signal-to-noise ratio and so on and so forth. And so these experiments so far have probed about a factor, about a factor of 2 in mass. And these experiments are going to be upgraded. Of course, I show a slide of one of the WIMP detection experiments that looks for the kinetic energy that's imparted by the scattering of a WIMP off a nucleus. And I think right now CDMS is the most sensitive experiment. And I believe this is their most current slide. So this is WIMP nucleus cross-section versus WIMP mass. And so here are the experiments that are sensitive to neutralinos, and here is the start of the parameter space favored by supersymmetric theory. And you can see, let's see, this is, I guess, CDMS's current limit. So the experiments are really starting to get sensitive, are probing the right place. I believe there was a seminar here in December announcing the most recent CDMS results that were provocative. So they have 2 events, 2 candidate events, and I believe they announced here that it was 20% probability that it's background. Looking at their data a little more carefully, I think that's gone up to about 30%. Certainly nowhere near the level for even evidence of, let alone discovery of. But I think the exciting thing is that these experiments keep getting more sensitive. And on here is xenon 10, that's the red line. And I think the next experiment that will move down considerably will be the 100-kilogram xenon experiment. So this is part of the full court press. This is a paper, I think, that appeared last week from the cogent collaboration, which is more sensitive to the lower mass WIMPs. And there were some provocative words in the summary of the paper and in the abstract about maybe this is consistent with an 8 GeV, very light WIMP that Dama is seeing. And I think, and then here's the spin-dependent results. And I think the COOP experiment is currently the most sensitive. So this, I'm trying to show the full court press. And then I'll end up here by showing Pamela. First an advertisement to calibrate your thinking about Pamela. This is a couple of papers that I was involved in the early 1990s, looking at the positron fraction. The data were not so good, but every time people measure the ratio of positrons to positrons plus electrons, the positrons are produced as astrophysics secondaries, and there was thought to be a well-understood model for how they're produced, and it seems like always the last data point is a little bit high and has big error bars, and so wrote a series of papers saying maybe this comes from neutralino or WIMP annihilation into E plus E minus directly or through W's and Z's. And recently, the data has gotten much better. Let's see. Recently, the data has gotten much better. Some of these old results. Let's see that the diamond. It's wearing out. The diamond are the points I was showing you before with very big error bars, and Pamela has much smaller error bars, and the last couple of points climb. Now, what's interesting about this, and the Heavenly Laboratory, which we started using more and more, doesn't always come with an instruction manual. It's not always as simple as it seems, and so people have been looking at this prediction for the astrophysical production of positrons, and there are more astrophysical sources than we thought. Maybe this is being explained by pulsars. This excess basically has been confirmed by the Fermi Gamma Ray Space Telescope, but what it's due to is not known. So here's my last slide, the dark matter decade. So I think I won't go out on a limb to predict that this will be the decade where we finish this dark matter story. But I think that this will be the decade that the WIMP hypothesis, that is a thermal relic of mass less than a few TeV, will be tested. Partly due to the LHC, actually largely due to the LHC, partly due to all of these capabilities that we have, the dark matter experiments, the Fermi Gamma Ray Space Telescope. Pamela, I should have put AMS up here because I think AMS will really help to clarify the situation. And I think, so the other thing I'm willing to say here is that I don't believe in MOND. I just want to end. So I like to publicize this. If MOND is correct, I will eat my PowerPoint, and that includes the laptop. So not just the memory stick, but the entire laptop, if MOND is right, because I know someone wants to ask about MOND. So thank you very much. So we have time for one or two quick questions, and next time I won't go over. Yes.
So what is actually, what's the status of amount prediction with respect to cosmology data other than just the flat rotational curves?
So
are they disfavored, excluded? Or?
So the original idea of MOND was this really brilliant observation of Morty Milgram that dark matter kicks in at a certain acceleration. And so then he said you could explain that if F is equal to ma squared. Now, you would like, that's not a theory, You would like that to be part of a larger theory. And a few years ago, Bekenstein and others have constructed a theory called Tevis that contains this Mond as a limit. But the theory is very complicated and not particularly attractive and not well tested. And so that's kind of the current status. I would say that often there are these hints in nature that turn out to be distractions. And another hint in nature was Fred Hoyle noticed that the energy density in the microwave background was roughly equal to the energy released by stars if they'd make the primordial helium abundance. And actually, it turns out it's very accurately equal, which is bad because it means the stars would have had to do it today and you don't have time to thermalize the microwave background. So often when we're studying nature, there are things that might look like a hint but turn out to be a distraction. And so the reason I put this up here is I think that the idea of particle dark matter is much more attractive. When we talk about dark energy tomorrow, if you're thinking about modifying gravity, I think dark energy would be a place. But in terms of dark matter, we've got these particles left over from the Big Bang. The attempts to come up with a theory that would get rid of dark matter have really been a failure. And so I think that path is not going to work. I hope that answered your question.
The picture I get is that dark matter clumps are together with galaxies, clusters. Do we detect dark matter without galaxies? Like where there is no galaxy?
I'm sorry, I didn't get the question.
Have we detected dark matter clumps where there are no galaxies?
Oh, is there dark matter where there are no galaxies? Yes. Yes. Well, yes and no. So what we know is that the ordinary matter follows the dark matter because of that 7-to-1 ratio. And we have indirect evidence that there are dark matter clumps that aren't lit up, that don't have stars. We see that from gravitational lensing. And so we suspect that, but the big clumps of dark matter, the baryons fall in enough and efficiently form stars. So I think that it would be very unlikely that you'd find something the size of our galaxy that was completely dark, where the baryons didn't light up. If we did, that would be a real puzzle for astrophysics. How come the baryons in something that large didn't light up? But we know with smaller clumps like 10 to the 5 or 10 to the 4 solar masses, star formation is not very efficient, and so the baryons don't light us up to tell us, hey, there must be dark matter here. I hope did that answer your question?
Yes, I think that's...
One more up there.
I didn't understand how you can put the limit on the axion masses by saying that you would have the condensate of axions. I didn't quite catch how you would put the limit on the individual axion masses if what counts is the condensate. I don't understand this.
So that slide, while I'm answering your question, I'll see if I can get back to that slide. So there's a variety of arguments that provide limits on the axion. So let's go right here where there's the dark matter, where there's this big condensate. So the condensate forms during the QCD transition. And you can calculate exactly how many axions form in the condensate. So it's not an arbitrary condensation. It comes from the misalignment of the vacuum. And so you calculate that, and that depends upon the mass to the minus 1.7 power. And so this band here reflects a theoretical calculation and the fact that we don't know how misaligned the vacuum would be, especially if the universe underwent inflation. And then these other bounds on the axion mass come from their influence on stars. But this one comes from the fact that it's not just axions that were already in the universe condensing. We have a mechanism for how this condensate was produced, and assuming that mechanism is correct, and I think there's reason to believe that we understand it, you can calculate how much mass density would be in that condensate.
think okay for today.
Okay, thank you. See you tomorrow.